Okay, so starting with a disclaimer, I just want to put out here that any opinions that we share are our own. We're not speaking for our company. So in the agenda, we're going to cover BIOS UEFI background, talk a little bit about the ecosystem and some of the business problems that gives us. We're going to talk about UEFI and BIOS security technologies, our data set and methodology, bug classes, a proposal for UEFI, and when we look at the 3 years of vulnerabilities, we're going to talk about how those are distributed by bug classes. And then we're going to talk about platform firmware threat modeling, and finally, what we expect to happen in the future. So, a little bit of background on UEFI. UEFI is short for Unified Extensible Firmware Interface. In old school terms, you're thinking BIOS. It's the first up root of trust of the system, and it hands over control to the operating system once it's done getting the platform ready for operations. And then the rest of the magic happens. UEFI membership does expand the complete compute spectrum. And you can check out the UEFI members at that link right there. So bottom line, UEFI sets up the platform to run. So where is UEFI firmware? As you can see, it's all over. We have BIOS and OS VMM share and access, but not trust. You have UEFI PISMM. You have the hypervisor that can grant VM direct hardware access. And a specific peripheral may have its own processor and its own firmware, which is undetectable by the host CPU OS. And then a personal favorite DMA or direct memory access. So UEFI firmware has to deal with all of these scenarios. So what's in UEFI? It's mostly written in C. Emphasis on specifications and standards compliance. So if you look at UEFI.org, it is a standard. It set better platform scaling, e.g. removes shadow ROM limits. It sets up storage, such as removes the 2.2 terabyte limit. CPU architecture independent, platform design flexibility. That's why it spans the compute spectrum. Secure boot solves trust-related integration challenges, and also has pre-boot networking, IPv4, IPv6, PXE, VLAN, and all your drive interfaces. And finally, the UEFI shell improves pre-boot testing and diagnostics experience. So once again, this is the root of trust for your platform. It's what's setting up everything to run. So, in terms of the UEFI ecosystem, it's an onion. You're talking layers within layers. At top of the onion, you have Tiano Core, which is the open source implementation of EDK II. After that, you have your IBVs, your independent BIOS vendors. Those are the ones that are actually selling BIOS to the OEMs that are producing systems. And then you have ODMs, original design manufacturers. Those also build systems that you can purchase. And finally, end consumers, the people that are actually running the computers and the last link in the chain that actually need to pull down and install BIOS updates. So if there's a vulnerability mitigation that comes out for the UEFI ecosystem, it has to navigate every layer of that onion. And as mentioned, there's also an update lag. Even if the IBVs, the OEMs, the ODMs all make BIOS updates available, the end user still has to take them and apply them. And there's a tendency in the world where end users are very hesitant to update their firmware. We all need to get over that. So here's a little bit graphical designation of what I just talked about. As you can see, Tiano Core is on top of the pile, and Tiano Core is solely built and maintained by Intel. It's open source. From there, it goes down to the IBVs, like we talked about before. You also have a reference tree, and then it goes to the OEMs. You've heard me talk about the ODMs, but then it gets, as you can see, the complexities are there. And then you have to ask yourself, and there's later presentations, there's been other firmware talks here. Are the ODMs applying updates? Are the OEMs applying updates? And finally, are the end users applying updates? It's got to go through every link of that chain. So, history. UEFI.org is a standards body. As already mentioned, it's a specification. About 2 years ago, the UEFI stood up a team called the USRT, which is short for Unified Security Response Team. And this is a sea change. UEFI for years and UEFI.org has always said we're a standards body. We're not going to take a position on implementations. They've stood up their own response team, and they are now taking a stance on implementations. This is a big change, and this is something that's happened in the last 2 years. So, a little bit of background on the USRT. This is composed by firmware engineers from member companies of the UEFI.org. To report a security issue, you can send it to security@uefi.org. Their PGP public key is publicly available, and this is a direct copy from their website. Provide as much information as possible. What are the product and versions that are impacted? What is the description of the vulnerabilities? What do we need to actually do to demonstrate the vulnerability, reproduce the exploit, configuration, peripherals, etc. And what's the potential impact of it once it is exploited? And any information that you may have on known exploits. So, as mentioned, Tiano Core is Intel's implementation of EDK II. It is eligible for the Intel bug bounty. So you can send a vulnerability report to secure@intel.com. We have a PG public key that's linked here. The bug bounty program we only launched this in March out at CanSec West. It's a private invite only bug bounty, but if you find a good bug and you send it into secure.intel.com, we will send you an invite. And note, you do need to be invited to be eligible. You can find more information on the Intel bug bounty online and our full participation guidelines at this URL right here. So, to recap, the bug bounty program is private invite only. It's a security and vulnerability is an open source implementation of Tiano Core that is solely maintained by Intel. We will pay for that bug. And that falls in the middle layer of this chart here. And you see it's up to $10,000. You must be invited by the HackerOne platform. We primarily leverage the HackerOne platform due to their pay system. It's really for lack of a better word, a PITA for us to pay an individual who might happen to be in a foreign country through Intel's finance systems. So with that, I'm going to turn it over to Vincent.
Hey, thanks, Bruce. So yeah, Bruce talked about there's the UEFI standard, there's Tiano Core, our open source implementation, and then on Tiano Core we have a project called the EFI Developer Kit 2. EDK II is maybe a 10-year-old software technology. All through the life of EFI, starting in '98, we had the EFI reference, then we had the original EFI Developer Kit, and then for the last decade or so we've had the EFI Developer Kit 2. And the two most important locations on Tiano Core are the core features, the GitHub Tiano Core EDK II, which you'll see on there, and you'll find a bunch of packages, like the MD module package, which will have the Dixie PI core that implements the UEFI and PI specs, which is a set of very generic code. We also have our security package, the networking code, the shell Bruce mentioned, on that location. In addition, a new area that we've opened up on Tiano Core is the platforms. So for both, and the point of EDK II platforms is to have instances of the rest of the firmware. In the past, some communities said Tiano Core was a sham open source project because you could grab a BIOS core, but you couldn't build a full product. And one of the things we'll talk about in a little bit is with this platform code and some other elements, you can snap this core into a platform and build a whole solution. So we have the core, but what if you do find a security bug? You can report issues to USRT, go to the Intel bug bounty, but also we coordinate or track our bugs through a secure Bugzilla. So there's an open Bugzilla with feature requests, generic capabilities, and then we have a secure Bugzilla. So HTTPS, you can create your bug entry. So this is where we track bugs, we keep them embargoed. People on we call our InfoSec list can view and help grade some of the bugs on the secure Bugzilla. And then once the embargo period is expired and we post the patch, we journal all the changes in the TNO advisory document, which we've just put on Gitbooks. So there's USRT, there's bug bounties, and now the EDK community, which is the a reference implementation of the EFI specs, has a Bugzilla. So that's sort of the ecosystem, how we track bugs, but what are some of the features? So in the EDK II world, we have a collection of defenses. The UEFI spec defines certain capabilities, and EDK II is our code. And sort of the gross taxonomy we'll use for the next couple pages here is what features did we do for protection, which did we do for detection, and which did we do for recovery. So this is sort of how we'll bucket the next few pages of capabilities we have with EDK II. So the first thing you'll find in EDK II is an implementation of a fully verified boot. So a lot of people say UEFI secure boot and I'm done. You know, I have security. That's really not the case. For a sort of a static verified boot, you need to have a root of trust and then maintain the verification up to the OS loader. So in the world of standards, open source, and hardware, this describes sort of the amalgam of the capabilities you need. On an Intel architecture, starting on the left, you'd have something like Intel Boot Guard, where the hardware can verify the first host firmware element. In our world, it would be something like a PI-based firmware volume. So Boot Guard is on the left, hardware, SoC-specific embodiment of the policies. And that first block of code, when you're now running your UEFI firmware, needs to maintain the chain of trust going forward. And so in our PI spec, we have examples of how to do the crypto verification into the DXE phase. DXE is our preferred EFI core implementation described by the PI spec. And at that point, you do the, quote, UEFI secure boot. So the whole point of UEFI is interoperability between shrink wrap OSs and platforms. The person who built your platform is often not the party that builds your OS. You want to have the ability to multi-boot many OSs. And so UEFI Secure Boot is there to provide that sort of interoperability between different OS vendors, pre-OS app vendors, and different board manufacturers. So the right-hand side of the flow is what EFI buys you. But from an assurance perspective, if you don't make sure your EFI core and implementation is correct, you could subvert a lot of these protections by attacking the underlying implementation. And as Rodrigo will show later, a lot of attacks aren't, we broke UEFI Secure Boot. They bypass a lot of these protections through other attacks. So Secure Boot is one. That's how we can assure the right operating system is loaded, but it works in tandem with Trusted Boot. So we work with other standards bodies like the Trusted Computing Group to define interfaces such that we abstract in the EFI phase how to access a trusted platform module. And so through that whole verified boot process we showed earlier, we record all the code that's executed into the PCRs. So Secure Boot stops and goes into remediation if it detects errant code. Trusted Boot measures or audits all of the flow. And so these are really two complementary features. And a lot of the upstream Windows, upstream Linux kernels, a lot of the OSs now have support for both of these capabilities. So Secure Boot and Trusted Boot are sort of the high-level features. But really, how do you build them? And so this is, what we wanted to do here was really show how, the standards are great, but if you don't reduce the standards to practice correctly, you can't get the value out of them. So our view of a lot of these features is to have an upstreamed, open source, product-ready implementation that people can just grab. And then also not only parties building system boards, but working with the security community, right? We want to, the only thing that should be secret is your private signing key off in some bunker somewhere. The mechanism, the code flows, we believe should all be open, transparent, such that we can get peer review and see if we're doing a good job. And so to that end, the Secure Boot, Measured Boot features talked about in the last couple pages. We have a full implementation on TNO Core. I mentioned the different packages we have. So we have one package dedicated to a lot of our security technologies. So you can grab that and get your measured and secure boot. And we've also documented sort of the design rationale behind it. So secure boot's great, trusted boot's great, but if you can subvert, again, the underlying implementation, game over. So updates is one of the big challenges we have with the industry. Bruce showed that tortured supply chain of how difficult it is through the different vendors to get updates to end users. You can't ameliorate all that through writing a few pages in a spec and some code, but one of the things you can do is remove some of the barriers to having robust implementation. So the government, with NIST 800-147 provides guidance on how you should do updates. And one of the things we added in the last year was, in the past, a lot of the ecosystem had their own update technologies, but we realized there wasn't sort of a least common denominator one people could just snap in and build a product. And so we've open sourced a full, crypto verified, rollback protected capsule update in addition to recovery. So the way capsules work is the operating system, UEFI exposes a runtime API with a well-defined envelope called a capsule that you can send an update to the platform. In the past, a lot of vendors had proprietary tools to do updates because they had different formats. But now, through Windows Update and in Linux, the FWUPD service, you can take these capsules where the envelope is well defined by the UEFI spec. Each vendor puts their own GUIDs, and you can pass device and system firmware up through this capsule mechanism. And if you're building a board or a device and want to provide this capability, in addition to the OS support, we actually provide now an implementation. You could grab off the web, it's permissively licensed, and have that and add this capability to your device. So secure boot, measured boot, and updates, those are the sort of the macro feature to protect the platform, manage the integrity. But in addition, when we did EFI in '98, really wasn't much concern about security. In the world of BIOS, you jump to your MBR, and EFI, you jump to your PE cough. As the years progressed, security became more of a concern, and so a lot of the capabilities that operating system software has been employing, we've been embracing in EFI. The trend now is as operating systems and hypervisors become successively more hardened. As you saw yesterday, and you'll hear later today, a lot of attacks are moving into the firmware. So we've been employing a lot of more defense in depth. No execute, some simpler variant of ASLR, stat canaries. Because when you boot, you have to boot and mostly look the same. And we also run one-to-one virtual to physical. You don't get a lot of entropy, but we do some randomization. So we're employing some now defense in depth technologies in the core. And then in addition, SMM. This has been a sort of a lightning rod of a lot of attacks. And so we've employed defense in depth, the ASLR, the NX on our upstreamed SMM infrastructure. If you saw Yuri's talk yesterday, he sort of cut off at the end talking about confused deputies attacking Windows 10. And his last foil said WSMT. The Windows S security mitigation table is an ACPI table that says you've built your SMM with a fixed COM buffer to essentially to help mitigate those attacks. We worked with the industry and have an open source implementation of that hardening. So the takeaway here is, as the threats against SMM have increased, we've increased a lot of the defenses, both in the implementation and working with the industry on explicating some of these defenses. And then a couple other things also you'll find on the web, and I sort of just got tired of you guys can surf through your web browser and find this stuff, but I wanted to let you know, we have user identity, password, APIs for random number generation. And again, capabilities that when you want to build your platform, we don't want people for basic defenses to have to invent something on the fly. We want to provide an instance of something like the lockbox interface. This is a way that you can hide the boot script for S3, which is one of the attacks that a lot of vendors have exploited. We have an example of that implementation on the web, in addition to how to lock variables. And then finally, EFI is a very modular, component-based architecture. We pull pieces together. It can be a little daunting, so we've tried to aggregate a lot of the best-known methods on how to use EDK II, and we've published that on the website. So I talked about SMM. SMM is really not part of UEFI. If you read the UEFI spec, it's a pure interface spec for consoles and block devices for bootloaders. SMM is a facet of AMD and Intel's architecture, this transparent execution mode. But it's very often used as a platform implementation, and it has been getting a lot of attention from attackers because of its godlike privilege. So we've really been trying to work with the community over the last few years, in addition to defense in depth, the fixed COM buffer, the other things I mentioned on the last page, on some what ifs on some other classes of protections, like the peer monitor, the SMI transfer monitor. This is something that can use the virtualization controls on Intel's SMM to deprivilege the SMM code. This is something that in 2009, I think there was a Black Hat talk, Joanna Rokowska said, I wish there was a reference STM. Well, we put one out there. So again, what we're trying to do through the open source is put the specs, put the code, let the technology, create a dialogue and an environment where you can then make some business decisions, as distinct from saying you should do this and having that supply chain workflow of closed source happening. We're trying to be a lot more open, and then is it the right approach? Embrace the security community and get feedback. And we got a lot of good feedback in 2015 when we did the upstreaming. Another technology that's not as well known, because publicly well known, but something we've disclosed as part of our with a lot of the manufacturers, is something called BIOS guard. It's another way to deprivilege the SMM, specifically access to the flash. So you can have a guard effectively, more like a hardware guard to mediate flash access. That's another technology we put out there, again, in response to concerns about SMM. And then finally, as you'll notice in that BKM document, we have a lot of guidance around the class of SMM attacks we've been observing, whether it's setting the range registers, locking SMRAM at the ready to lock event, which is when you're about to run third-party code, and then some of the mitigations around the COM buffer for the confused deputy, rebarring attack, make sure that you don't statically decide which MMIO to use such that if attacker changed it. These are guidances we've put out there, and we demonstrate. And some of the other things, Bruce mentioned DMA as a concern in some areas. Been exploring DMA protected boot, using things like busmaster enable to provide least privilege, and then exploring using the IOMMU to see if we can harden the boot path. But these are a lot of things. It's daunting. If you read a BKM document, you'll say, man, that's a lot of stuff to keep up with. And so really, the thing we're trying to do, and this is the progress we've made so far, and we're trying to provide more, is, could you build the whole solution? Could we demonstrate this? Grab a board, grab a tree, build the whole stack. And to that end, for both Atom and core-based platforms, in that EDK II platform repository, you can essentially build an instance of a platform. Take the platform code from that directory, go to the EDK II repo to grab the core. Some things we're not able to open source yet, so we have a well-defined binary blob called the Intel FSP, but it's publicly available, no NDAs. So grab some code and binaries off Git, build a firmware, and then hopefully through that we're demonstrating this is how you should put the pieces together correctly. Beyond building the platform, there's some really good training on GitHub from the ATR team that talks about ChipSec, which is a tool that you can run a posteriori on your platform to see if all the locks are configured correctly. So again, open source core, some platforms, guidance, and then even tools you can run to see if you, quote, did the platform correctly. With that, assume an ideal world where we did everything correctly. What have we observed in the industry? So Rodrigo is going to talk about some of the issues found in the industry.
Thanks, Vincent. Hello. Can everybody hear me? Yeah? Oh, okay, cool. So yeah, we trying to put defenses out there, right? But we see researchers keep publishing bugs, bug after bug, right? In different components, different products. Are those against the state of the art of defenses? That's a question that we want to give to the audience, right? So help us to actually test the state of the art. Help us making the state of the art known. So when anyone fails, point out the failure, but also point out the state of the art. One of the things that we intend to do now in this part of the presentation is try to show a little bit of the data set that we have, all the bugs that we're seeing for the past 3 years, and basically share a bit of like what are the findings like and how they classify. Hopefully this will help everyone to actually get more familiar with like a BIOS related vulnerabilities, and maybe like start also helping auditing and understand that this is not magic. Even though there is a lot of things that are like platform specific, most of the bugs are still like traditional normal code bugs that anyone that has like code understanding and code auditing abilities would easily be able to help and contribute as well. So before I even start showing the data, I really want to point out to a presentation by Mitri guys and OSF, actually it happened in Black Hat 2013, where they talk about like bias in data sets, right? They basically explain why it is so difficult to really account vulnerabilities and how to compare vulnerabilities and how the different databases look into vulnerabilities in different ways. So I want to make clear that everybody understands the limitations of the data that we are presenting here. So the very first thing is like this data is coming from Intel pcert database. That means if something was not reported to Intel or was not known to Intel, it's just not there, right? For the past 3 years, there was 124 issues that were actually somehow generating a case. So just to be a little bit clear, like every issue that generates a case might end up being a known issue, right? So these ones that were known issues, we ignored from the data set. Also, there are a lot of cases that are actually opened by internal teams. The huge majority of UEFI-related vulnerabilities are being found by internal teams. So those are also part of pcert if they do affect a product that is released. If we find it before the product is released, if it doesn't affect any platform that is on the market, it's not going to be there. Obviously, internal teams, they are not perfect. So multiple times they might find a bug in a new platform, but they don't even realize it affects an older platform or a released platform. So that will not actually be part of this data set. I want to say a little bit like some researchers also like to report bugs to us, even though they know the bug does not affect specifically Intel set, right? So the bug is specific to one OEM, but the researcher do report to us. Those also get into a case, Intel pcert case, and we really appreciate researchers doing that. And oftentimes, more often than not, we actually help the researchers to coordinate that issue, to even have the discussion with the OEMs, and we sometimes even provide like sentences on, hey, why this is indeed an issue, and help that. So keep involving us. It is actually really good, and at the same time, we hope we can help back as well, right? Given all these limitations, another thing that happens in the pcert data set is if we find an issue and that issue affects multiple platforms, we tend to group that in one pcert. But that don't necessarily happen in the past 3 years. So there were cases where there were multiple different like spin-off of pcert issues, and we try to clean that manually, but that happens. Also, because the internal researchers tend to basically bundle together a bunch of reports and send us one, it's very common that a lot of vulnerabilities are reported as one case for pcert. So when it was very obvious for us, we split that, but when it was not obvious, we just actually kept the bundle together. So with that said, in the end, like really real issues that were reported in the past three years and were fixed were like 77 issues. I say past 3 years, but we started counting January 2015 and stopped counting like a week ago, right? So you have like 2.5 years actually. So given that there is so many problems in the data set, I think like everybody will ask, hey, so is that even useful information, right? So we think it is, but not to really compare one platform to the other, because as I mentioned, like this bundling together and as Bruce and Vincent demonstrated, the way that the ecosystem works, if we do fix something in core, it ends up fixing everywhere. So we might not have counted that as a given platform, but maybe it actually affected that given platform. We also believe there is value actually to define a taxonomy, right? So we try to provide a classification for BIOS bugs to help like into the discussion on what is a BIOS bugs, what are the kind of issues that we see in BIOS. We also believe that helps defining next steps and future strategies, right? So we also doing that. So we propose some future changes and like some engagements that the security community can help, what customers and end users can also help, right? And how we can try to make the entire ecosystem evolve. Maybe it is good data to actually show trends. So you can see that there is some more researchers are looking into it. So, but don't count that as, hey, there are more bugs now than there were in the past, because that's just not going to be true, right? It's just the fact that more people are looking into it now, right? Also, like we don't think that this data set can be used for that purpose of like comparing the number of bugs that we have now versus the past, but it does show the trend of more researchers focusing on it. And also more attention by Intel. Before I explain a little bit about like the proposal for the bug classes, let me just say that there are like hardware bugs that do affect the promises that or the expectations you have from the BIOS on the platform, right? So there are like some of those bugs became classic, right? So the memory sink hole work presented actually in Black Hat 2 years ago, that became a classic bug. So that was a hardware bug, but it did affect somehow the way that UEFI was actually providing you security. So we did define a class for those bugs, but they are not on this 77. Okay, in that 77, when we're showing the numbers, we did not count those, but we defined a class for hardware bugs because they also affect, of course, UEFI and biosecurity. The only matter is like there is not much that end users and researchers can do on those ones. We need to be able to patch and be able to deliver the patches to the platforms. So I gave some examples of like ones that became like kind of famous, right? So there was the famous one exploited by Joanna and Rafal, where it was like when you enter into SMI, when actually you're handling an SMI, the caches are synced back and you overwrite memory that's supposedly protected. And the diffuse one that was presented in Zero Nights past year, where basically bootguard was badly configured. So we also do not trying to do like a bug classification that is super comprehensive. This is not an academic exercise on taxonomy for firmware issues. Maybe someone should do that academic exercise. What we try to do is really a very simple list that for all the issues that we saw, like for defining the bug classes, we used the issues from since 2007, even though for the numbers that we counted only issues from 2015. But we wanted to make sure that the bug classes that we're presenting indeed cover all the issues that we found or we encountered in BIOS. So we hope that like it is kind of good, but it's not an academic exercise. You will see that some of those classes we put like lots of normal software vulnerabilities in one big class. It's not validating trusted input is the name of that class. And of course that can be explored a little bit more in details, but we didn't care much about that because the idea is like to be something very specific to BIOS and to be able to generate this discussion with the community. So the bug classes, like, so we divided in 7 different bug classes. I know it's a bit small for people on the back to see. Don't worry about that. I will give examples for each of the class. Here is just the list so we can, like, everybody can have their expectations set. So we define like inconsistent power transition states. So essentially there is it's very common. One of them was the S3 boot script, but there are many other bugs that in a sense is your machine when it's actually doing like a warm boot behaves different than when it's actually doing a cold boot. So either because some states are lost, some locks are not set, it's a different path that is taken. This is actually very hard to define and to compare and to validate that like different like cold paths are actually performing correctly. So we classify that as one specific issue, and the S3 boot script, we define it as one of like the main topics inside that bug class. So race conditions are another one. Even though race conditions are like very common software bug, here because you do have like hardware that is initialized as well when the platform is booting, and you might want, for example, to have DMA protections as Vincent was pointing out, and some hardware might have actually already loaded. So this is a class of issue per se, and we defined that separately. The basically input that should be validated and it's just not. That is something that affects a lot, like lots of the SMM related bugs are related to that. So you're receiving an input and you are not properly validating it. As Vincent discussed, we're adding more and more mitigations to try to make the general classes a little bit harder to exploit, but they are still one class. measurement failures. So this is when secure boot somehow fails you, right? There were like the most classical issues there. Like I will, like when we get into that specific one, I will show like 2 interesting examples that are really bad failures from our side. And then like I think it serves as a good example on how, like sometimes secure boot might fail you and what you can do to look for bugs there. We have like the platform capabilities not properly configured. That is like a huge, right? Unfortunately, a lot of the current guidance that Intel gives in terms of like what is the security of the platform is under NDAs, and it's only given to OEMs. And then the OEM can, of course, make their own business decisions if like they should follow that guideline or not. And sometimes it's even harder to find the guideline. And sometimes what we write is not necessarily super well written, and people interpret it in different ways and end up being bugs. We do have like some news here. Soon, Intel will be releasing that guideline to the bigger audience, to the bigger public, specifically the security part of the BIOS Writer's Guide. So more researchers will be able to help developing test scripts, testing code, and of course finding more and more bugs, right? And well, that's all Bruce's problem anyway, since he's the P-Cert guy, so send to him. Then, of course, like another big class that we've been seeing, and it's growing lately, is the security of meaningful assets are exposed to untrusted entities. So imagine here a scenario where, for example, you have an UEFI variable that controls if secure boot is enabled or not, but that variable is exposed to anyone. So that's the same as not having secure boot on that platform. So this is the kind of bugs where like you're exposing multiple ways of doing certain configurations, and then the configuration itself is not as well protected as the feature per se. And then, of course, as I mentioned, the hardware misbehaving. This is something that we did not count in the bugs, but it is a class per se. So to actually give examples for each of the cases, right? So I think the S3 boot script vulnerability was very well stressed out. So there is like public exploit for it. It is a very interesting one if you want to start playing with like running your own code in SMM, and if you want to start actually playing with platform, this is one that I think it's really good. And it also helps you validate other thread models, right? If you want to try to do attacks from SMM to something else, or if you want to see when the platform fails, what is breaking in your assumptions. So I think that's a good one for looking to that. There's like many other like bugs that happen in there. So one that we recently actually fixed was basically like related like to power transition as well. So imagine that when your platform was actually booting from like code boot, like the platform like initialized some data structures, and the code was getting those data structures put into protected memory and then parsing those data structures. So when the platform was actually coming back from sleep, the OS was actually generating the data structure in a different way for the code to parse, and the code never actually copied it to trusted areas before actually start doing the check. So it checks, but it is in an area where the OS can actually go and modify. So this is a bad thing, right? So and that was another one that like it was inconsistency between like 2 different power transitions. So going for the race conditions, right? And one thing that I forgot to say when I mentioned about the bug classes, you see that some bug classes, of course, like the same bug would fit in 2 different classes. We try to actually get into the root of the class to put that bug. So the example was this one that I just gave on the power transition. In the end, there is a race condition, right? Because you're accessing the data, and the data can be modified after your check. But the root cause is because there is 2 different like states that are doing things in a different way, and one of them is failing, right? For the race condition, a good example is like, for example, there was another bug that we were loading an optional run from a third party before the end of Dixie, so before actually the locks were set and the platform was protected. So this is a very bad thing, and that actually leads to bypassing of your secure boot and other things actually in your platform. A good example of race conditions are like all those that are like for example, like an SMI handler is looking to something that is outside of SMM memory. It parses outside, therefore it's a memory that is not protected, and then all the checks are bypassed. So those are like getting more and more common. So we're doing some experiments on trying to actually tackle those automatically. So Joru from Google Project Zero released a very nice work like a few years back, box pound, and actually actually in this black hat represented like a reloaded version of it. And what we did was like we got his work and we implemented that in Simix, the simulator, and we're trying to automate that to actually find the same cases, but now for SMI handlers. So part of that work, the Simix plugin that we wrote and everything is open source, and it's available in the latest POC GTFO, the POC GTFO 15. Same thing here, like trusting input. This is like the more traditional bug, like bug classes like that everybody should be aware. So researchers should have no problem in finding those. We did present like actually in Zero Nights past year some advances in that area as well. It's a project called Excite, where we're trying to do symbolic execution of BIOS. There is also a good paper that was presented even before the Zero Night work, and it's another one that we're trying to automate more and more, finding those kind of bugs on top of the mitigations that Vincent already mentioned. So for the measurement failures, there is like two ones that we included here as really interesting examples, because this is the kind of thing that sometimes people just take for granted. And of course, when we look in, we also have our own limitations, right? So for example, like a client and server platforms were sharing the same key. So you would be able to get like a BIOS that supposedly loads in your server parts and you load it in your client part. But now the client part breaks because basically it's not the correct BIOS, it can't initialize the system and your platform doesn't boot. But because it's all signed, it's all good, you can use all the update mechanisms to actually load that BIOS, right? That is a big failure. And of course, then like we hope that we can find more of those and fix. Another one was like there is terse executables that are supported by Secure Boot. And basically, like when it was loading it loads, it sends to the TPM for actually doing the verification. When TPM goes for extending the PCRs, it did not support this kind of executable, so it basically returned an error, but Secure Boot ignored that error and just continued as if it was actually checked. Therefore, you could load those without actually any signature checks. So the other class of bug is like platform properties not properly configured. So this one was like it is really big, right? So we like released chipsec like a few years back and keep working on improving that, like to make sure that like this kind of bugs are basically caught. There will be a talk like at 5 p.m. by Matrosov that basically will show another one of those cases that like OEMs failing like to actually follow like the stuff, and he did an amazing work actually exploiting it and demonstrating like what you can do when something like that fails and what is the impact in the platform. So then we like the security of meaningful assets, I already gave the example, is essentially if you have something that controls something else, the control itself is exposed to untrusted entities while the control works. Some untrusted entity can just change the configuration of it. And finally, the hardware misbehavior is the classical classes that we already discussed, right? Like the memory sinkhole being a great presentation as an example of like, hey, I was yesterday in a dinner, someone asked me, hey, how hardware can fail and affect security, right? I think the memory sinkhole talk is a good example that like has a lot of details if anyone is interested in seeing that. And of course, you can see Intel erratas. I hope we do a good job like making the erratas available and making the patches available as well, but like you can always look at there and try to learn things from there. So this is the bug distribution, right? Just like to show. I know it's a little bit hard probably for people who are in the back to see, but the big area here is the untrusted input. So basically it's classical software vulnerabilities like buffer overflows, integer overflows leading to buffer overflows, things like that, or straight getting a pointer from some entity that is untrusted. That is the huge majority of BIOS issues. So any researcher that is interested in doing it can start contributing immediately. Just get the Tiano core and start like looking for bugs. That's the biggest class. And the second biggest class actually of issues is really misconfiguration. So we hope when we provide like when we open like these guidelines, there is more people looking to all these different platforms that are available and finding these misconfigurations. We hope researchers help us like running chipsec in all kinds of platforms available and all to actually start finding more and more of those, right? Those are the huge majorities. If you look like for power transitions, we have like a big pick But that's essentially because when the first S3 boot script work was found, then of course more people start looking into this kind of bug and we start finding more issues. If we look into the distribution per year, you will see that, so just for people who can, if you can see on the back, the yellow is 2017, then we have like the gray is 2016, then this color that I have no idea what is this color is 2015, and the blue is the total. It's just to give an idea of the proportion of how the issues are changing. So you will see that like we have like some peaks from time to time, and that actually also shows that, well, Intel does care, right? If you do find something, and if it is like a new trend, there will be a lot of eyes that will start looking into that as well to try to find it, to find other cases and patch. So yes, please keep working with us. So let's say, like, what is the rationale for developing a threat modeling when there is so many classes of bugs?
Right, thanks, Rodrigo. So yeah, so the challenge you've seen with the supply chain, code bases, different platforms, the spec, a lot of the modular code elements you put together. How do you decide what to test? Where should you add new defenses? And that's where you really need a threat model. And so really it just defines the goals of your security solution. And so one of the things we want to engage more with the community is having a more public threat model, both on the assets, the threats, and the mitigations. This is a very schematic one, very high level. Our threat model has been evolving over time. You'll see SMM was to defend itself, back 5 years ago. Now it's make sure the SMM doesn't attack the hypervisor. That shows you need a threat model and then a way to discuss with the community a way to evolve the threat model. So threat modeling is something, again, just as we put more code out there, more platforms, we want to have more public. But I want to give a couple minutes for questions, so maybe let Rodrigo take us home here with the future.
So yeah, I think like this is a call for actions, right? We're publishing a lot of code, we're publishing a lot of materials. The presentation is available, there is references to everything that is being done. Help us to make sure that everybody understands like the state of the art, help us reviewing it, and now ask questions.
This is golden.
Please.
Newbie question, where's AMT?
Oh, so the question was, where does AMT fit into this? So Bruce showed earlier that EFI is the host firmware, and then he talked about also device firmware. So AMT would be a class of device firmware that runs on a microcontroller in the chipset. It's complementary to the host firmware like EFI such that they talk to each other, but AMT is a wholly separable execution domain. That's a good question.
Yeah, there will be a talk on AMT in 1 hour.
30 minutes.
30 minutes. Oh.
What's the process for releasing patches and how are you going to apply the patches?
Couldn't hear the question.
Oh, so the question was, what's the process for releasing patches and how will you provide patches? So there's many answers to that. So a lot of the system board manufacturers will curate the patches themselves. Perhaps today they put it on their website. In the future, we're hoping it's distributed through Windows Update and FWUPD. Source code patches, like when we find bugs in the open source, they're on a commit list, and we also backport them to supported branches and journal them in the advisory log.
That's kind of where we get into the onion part that I talked about earlier. We'll roll out patches that then have to go to the IBVs like AMI, Phoenix, Inside, etc. From there, it has to go to the OEMs, and from there, it goes out finally to the end consumers. So there's multiple levels there in the ecosystem that it has to go through.
I'm sorry?
SMT, the limitation.
Oh, the limitation. So the question was, talk about the limitations of SMP? A symmetric...
STM? STM?
Oh, the STM.
STM, yeah. Sorry, no, yeah, sorry, I should have understood.
Acronym overload, yeah.
Yeah.
So the STM is a hypervisor that runs in SMM. I think the limitations, it's, the ultimate, the Anderson report for 72, the ultimate security is a reference monitor, right? It's a hypervisor. But I guess the limitations are as much business as technical, meaning a lot of, even though we have an open source STM, a lot of vendors don't include it into their product BIOS. So most SMM implementations today run in Ring 0 and SMM, not underneath an STM.
Also, I think, like, of course, complexity, right? If you have like a bloated hypervisor there, then it will have bugs as well. So the question is, there will be more bugs on that hypervisor and the original SMI like handler that is being exploited, and the privilege is there. So it's always a challenge question, right? So, but I think that those were like the biggest two limitations.
Yeah.
So can you talk about T-boot and secure boot working together? Is that new? And I mean, is that happening now, or is that in the past T-boot and secure boot?
Oh, so that's a good question. So we could talk about T-boot and secure boot working together. So what I described today was trusted boot and secure boot, which are both BIOS features. But there is an open source project called T-boot, which is used for Intel trusted execution technology. The T-boot project historically was using multi-boot grub on a PCAT BIOS boot. That's moving to UEFI boot, and we're working with the maintainers such that you should be able to compose UEFI secure boot, T-boot, but there are still some opens there. But yeah, we would like to have a point where all these hardware and firmware protections and ingredients can work together, but there is some work on T-boot to be compatible with UEFI secure boot. So that's work in progress. It's a good question.
Thank you very much.
I think we're done.
Good question. So is there a place for SGX in something like firmware? So SGX runs in Ring 3, UEFI runs in Ring 0, but perhaps you could do a reverse trampoline and use some SGX in the pre-OS maybe for pre-boot authentication, because doing passwords and other things where we have to protect content, we invariably push those flows into SMM. SGX may be an option to factor some of our pre-OS applications. Sure, yeah.
And we're out of time, so if you have any additional questions, you can follow us over to the room.
Thank you very much.
Thank you.